Okay, so now we're going to talk about how we locate an earthquake. And to be very specific, we locate the origin of the earthquake, the point on the fault where the earthquake first starts. And we do that using the both P waves and S waves, and we take advantage of the fact that they travel at different speeds through the Earth. So we'll call the speed at which the P wave moves through the Earth alpha, and we'll call the speed or the velocity of the S wave beta. Now, we can measure on a seismograph the time that a P wave arrives at our station. We'll call that T sub P. And we can measure the time that an S wave arrives at our seismographic station. We'll call that T sub S. Now, that time, remember, that time is just some time on the clock. It could be 2 minutes past noon today. So it's some arbitrary time that we measure actually with a very precise clock. We want a very accurate clock. The time that the P wave arrives is going to be the origin time of the earthquake, that is the exact time that the earthquake initiated, and the extra time it took for the wave to propagate to reach us, and that's this term here. So if the earthquake origin is distance x from our seismograph, and alpha is the speed at which the wave propagates, this is the extra time it will take for the P wave to arrive at our station. Similarly, the time that the S wave arrives, now it will arrive later. It's the secondary wave. It travels at a slower speed. So it will also arrive at a time given by the origin time of the earthquake plus the time it takes for the wave to propagate, and that is the distance divided by the time, the speed that the S wave propagates. So what we can measure is the arrival time of the P wave, the arrival time of the S wave. What we don't know, the things that we need to solve for are, oops, I was trying to make that a different color, is the origin time of the earthquakes. We don't know when the earthquake started, and we don't know how far away it is, distance x. So you can see these represent two equations and two unknowns. The two observations are T sub P and T sub S, and the two unknowns are the origin time and the distance. So now we just repeat those two equations that we had from the previous slide here, and let's subtract one from the other. We'll subtract the P wave arrival time from the S wave arrival time because this is always larger. S wave always comes in later. And the nice thing about doing this is that the origin time of the earthquake cancels out. You can see this term will cancel this term. And we're left with just the distance over the S wave speed minus the distance over the P wave speed. We can do a little algebra to put this under a common denominator, and that will give us this expression here. So the difference in the travel times, or the arrival times, is the distance times this factor which depends on the wave speeds. Now we're going to assume for the time being that we know how fast that both the P and the S waves propagate through the Earth. That does depend on the rock type, but for the most part we know that reasonably well, or we can actually estimate that using other kinds of information. So let's go to this equation again. We'll go back to this equation now and rearrange it to solve for the distance in terms of our measured arrival time difference, the time between the S wave and the P wave arrival, and this factor which depends on the wave speeds. So for typical values in the Earth's crust, P waves travel at something like 6 kilometers per second, and S waves travel much slower, about 3.5 kilometers per second. So that gives us a crude rule of thumb. That is, if we take the time difference between the S wave arrival and the P wave arrival and multiply it by 8, we'll get the distance in kilometers away. Or if we wanted to do that in miles, we would multiply by 5. So if we can measure the arrival times of these waves at a seismographic station, we can determine how far away the earthquake is from that particular station. And for those of you that grew up in areas where there are thunderstorms, which probably if you grew up in California you may not be too familiar with, but if you grew up in areas where there are thunderstorms, you may have as a child counted the time between when you saw the lightning and when you heard the thunder and multiplied by the difference between the speed of light, which is so fast that it's nearly infinite, times the difference between the speed of light, that is the lightning traveled, and the speed of sound in air, which is the speed at which the thunder arrives at. So this is basically the same idea. We're measuring the time difference between two waves that travel at different speeds, multiplying it by a constant factor to get the distance from the seismographic station to the earthquake source. So here's an example where there's a P wave. We can see very clearly the P wave onset here. The S wave is a little harder to identify, but it's been located here for us on this seismogram. So about how far away is this earthquake in kilometers? We'll check in class and see what people found. So, in order to find the epicenter of the earthquake, we would need at least 3 seismographic stations. Here's a station here, station here. If we know the distance away, here this is written r instead of x. We've been writing this in previous slides as x, but it's the constant factor times the difference in the S wave arrival time and the P wave arrival time tells us that the earthquake source is somewhere on a hemisphere located here, which we would draw on the projection of the Earth's surface as a circle. If we had the distance to 3 seismographic stations, then we could find where they intersect, and that would be the epicenter of the earthquake. So that's one way to locate earthquakes, and that actually is used, but often seismologists locate earthquakes using only P waves. So why not use S waves? Well, we like to use S waves if we have good recordings of S waves. Here you can see, if we back up, that this is a pretty clear S wave onset. But many times it can actually be quite difficult to pull out the onset of the S wave, whereas the P wave, because it comes in first, the trace on the seismograph is usually very, very flat, and it's very easy to determine when the P wave arrived. Because the waves bouncing around in the Earth, P waves bouncing around in the Earth, may not have died down yet when the S wave arrives, it can often be difficult to determine exactly when the S wave arrives. So we can locate earthquakes using only P waves, and I won't go through the algebra, but we'll just give a little flavor for how that works. We're going to need at least 4 stations to locate an earthquake using P waves. So I'd like you to think about why we need 4 stations. Let's think about the number of unknowns that we have to solve for. So here's an example from the Bay Area. This is an earthquake recorded by the USGS seismographic network. And you can see, here are seismic traces. You can very clearly see when the P wave arrives. The time is indicated on each of the traces, and the line points to where the station is. So we could find a location and origin time consistent with all these P wave arrivals. And the distance, again, as we saw before, the arrival time of the P wave would be the origin time. The origin time is the time at which the earthquake initiates, and the time it takes for the wave to propagate from the earthquake to the seismographic station. So that's, again, the distance divided by the wave speed. So in this particular example, it shows 1, 2, 3, 4, 5, 6 seismographic stations. So we would have 6 measurements of P wave arrival time, and we have only 4 unknowns: x, y, z, or latitude, longitude, and depth, and the origin time. This really should be T0, that's the origin time. So in this case, we have an overdetermined system of equations. We have more observations than we have unknowns, but we can solve that in some way using mathematical methods called least squares to find the best fitting value of the position and the origin time of the earthquake.